For with eyes pink.
Welcome, Jamie. Alright, we went over the test, Jamie, so I will probably send you pictures of your test later on today. So make sure, checking your email. If it's not today, it'll be early tomorrow. So go ahead and have your homework out so we can go ahead and go over it. You just had to set one problem on page 96. So sketch a way to label the amplitude, wavelength, and frequency, and then define the terms in words. Alright, so
I went ahead of all y'all. I did wavelength, amplitude, frequency, and wavelength.
Oh,
good job. Alright, so most of your waves probably look like this. Loosely. Alright, so what is the amplitude first off? Alright, Chris, what you got?
Yeet, draw a thing through the middle. That's amplitude.
Okay.
That's amplitude.
From just the spot?
No, in between like the frequency or the
Like that?
Straight gas. Draw a line through from one point to the other point. From the end point of one wavelength.
That? Come draw it. Where? Where you at?
That's still wrong.
That's the same thing.
That's the same thing you just.
That's a good try though, Chris. Alright, so
My turn.
or Ethan, what do you got? Y'all just want to be on the camera.
I don't know.
Hey.
You can't touch it. Wait, you can't touch the same chalk Chris did front. You
No.
touch this chalk.
It's wrong.
Right now, always by each other. I had this. That was it.
Which point now?
That was going up. That's the amplitude.
The top? The top part of the wave?
Amplitude is the wave strength. So that can't be amplitude. It's the wave strength.
It's
So
not
yeah.
through the definition, but nope, that's not it.
Alright,
Alright?
my turn.
Not quite. Ethan, you have a good guess though, but that's not quite it. Alright, questions.
Come on, win.
You gotta get a different piece of chalk button. Can't touch Corona chalk. I'm sorry.
We're out in the hallway by each
Corona's
other.
new product, Corona straw.
But that's what I mean.
Okay, oh, I'm sorry.
It's got coronavirus inside.
Alright. Quentin is correct that yes, it's the halfway point to the top or halfway point to the bottom. So it's not from one wave to the next wave, that's wavelength. So we'll talk about that in a second. But you are right that it is wave street. It is the idea of wave street because which one has stronger? A tsunami or a wave at the beach?
A wave at the beach.
A tsunami and a wave, regular wave at the beach, Ethan.
Ooh,
Tsunami,
Tsunami.
because it has more height, if you want to think of it that way, to where its amplitude from the midway point to the top is a lot greater. So that's the reason why if you have a taller wave, that's the reason why it has more strength. Okay, yes, Quentin.
I'll deal with that.
Yes, go. Because your eye is red and I don't want to.
That's why when you get hit with a tsunami, you get ripped into a million pieces.
Okay,
When you-
let's make sure we're being perfect. It's going on YouTube.
But when you get
We
hit,
love blood.
but when you get hit with a wave, you just maybe get knocked down if you're weak. But yeah.
Okay, let's go. Alright, so the next one. So amplitude, wavelength. Alright, Chris, what you
I
drew
don't-
was the wavelength. So from one point to the next point, that is a wavelength. So like for this one, I just drew it from crest to crest,
Can
because
you
that's easy. But you can do it your way as well. It's basically from one point on the wave to the same point on the next wave.
I
Can I do
did
frequency?
That works. Alright, what is it, Ethan?
Can I do frequency?
Okay, what is frequency?
I do wave.
Number of successive waves.
You know that come high at a given point. Oh,
Three.
you're supposed to label sketch a wave. Oh, you're supposed to label the crest and the trough as well. What's
What?
the crest?
It didn't say that in the question.
Sketch a wave. Oh, okay, so what is the crest?
Z top of the top of Z wave.
Good job. So yeah, so the crest is what Ethan was pointing to whenever he drew it. Alright, what is trough?
And the low of the truth.
Z thing, yeah, what's Z top of?
Yeah, and if you want to think of it that way, hey, that helps you remember because it does make that same shape like a feeding trough. If that helps you, then yeah, use that. Alright, so amplitude, just make a note of that has the difference between the crest and the trough of the wave, that halfway point is also the measure of the wave strength. Wavelength is the distance between any point on successive waves. Frequency is the number of waves that pass by a given point of time. Alright, anyone have any questions about that?
Nice.
Alright, so let's go ahead and let's get into it with chapter number 7 now. So
Is
if
it math?
you, what?
This is mostly math.
This one is not mainly math. So if you hated math in the last section, this one
Yes.
is more memorization. Now there is a
Mamma
little bit of
mia.
math, but you do
Mamma
have to
mia.
memorize it. So if you were struggling with terms in the last chapter, Start working now so you can fix it.
Looks like I'm good this chapter.
Hope so.
What is the pitch?
It is page 93. Alright, so your book points out that we've been talking about the mathematics with chemistry and how we work in it with thermodynamics. Now we're getting into it with why do chemical reactions occur the way they is. It has to do with the electrons. That's one of the major reasons why you have the elements, why they combine into certain ways. Anyone remember how many electrons a compound typically wants to have, or how many valence electrons in particular that an atom typically wants to have? This does fluctuate a little bit. That typically is a typical rule.
1,
8.
3.
Are you saying it or 8?
8.
8, so you're right, with the octet rule, typically they want 8. So scientists were discovering, okay, that yes, it has to do with the number of valence electrons. That's why you have compounds react the way they do. Now, electrons has a lot of very similar properties to light. That's when your book kind of takes a step back and starts talking about light, electrons, and atomic structure. So this chapter is interesting because it kind of takes a break from math. So it knows that the previous chapter was kind of a doozy. So it's taking a break from it, but okay, we're going to go back and look over more terms and definitions. Let's read why we go back and look at light really quick. Okay.
Let me guess, next chapter is going to be math.
The next chapter, if I remember correctly, this one has application in it. So this one's not necessarily math, but you have to think your way through it in some parts of it. While this part in particular is just looking at just memorization. Alright, so make a note. A wave is described as a periodic back and forth motion that transmits energy. So make a note for that, for what a wave is. It's described as a periodic back and forth motion that transmits energy. Alright, so how many of you've done this with either like a jump rope or maybe a piece of string where you've tried to like pop it to see how far you can get your wave to go down it?
It's me.
Okay, just you? No one else has done that? Okay.
Done with the vacuum cleaner.
Okay, you've done it back before. So
Here.
you will know that you can pop it or get the wave to go down. Now, whenever you do that, does the entire cord, is it supposed to fly out of your hand whenever you do that?
Yes.
No.
No, it's not supposed to. If you're transmitting your wave energy probably with your wrist, whenever you're popping it, you'll see the wave motion, but the cord should not fly out of your hand. If the cord of the jump rope flies out of your hand, you might injure somebody or injure something. So that's the reason why it's not supposed to do that. So that's why this one is transmitting energy, but it itself is not moving in the direction that it's transmitting energy.
Isn't this dual purpose as Z battle ropes?
What?
Z battle ropes.
Okay, say it correctly.
Battle ropes, like that.
I've never done that.
Never done
I've
battle
never
ropes. You guys
done
ever done battle ropes?
that.
I don't think so.
It's like really big things. You know, like Coach One, like woo 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 woo.
Z battle ropes.
What?
Z
I
battle
don't
ropes.
know. Maybe I just can't picture the right
It's
thing,
like
but
in
it
a
doesn't.
Yeah.
Oh, maybe that's why.
The Z battle ropes are cool.
Alright, so yeah, so that would be the same height. So are you supposed to let go of those then?
No, you're not actually. 'Cause
I'm
if you
pretty
do,
sure
you
you're
can
not.
Get, you can get no kid syndrome if you do.
Oh, okay, let's be appropriate. But yeah, that sounds like that you're not supposed to do that. So again, you're transmitting energy with your body, but you're not supposed to have the cords themselves move or the rope itself move in that regard. So that's the idea of a wave. It's that back and forth motion or up and down motion, and it's transmitting energy, but it itself is not supposed to move. So a couple of terms to note for it as well. If you're making note though of what a wavelength is, we've already talked about this, but this is from one point on a wave to another. It could be anywhere on the waves, but the crest and the trough are the obvious place to put them. That's kind of most drawings do there. So if you want to do it in the middle of the wave and go from like here to here, okay, yeah, that works, but it's cumbersome, so most people don't do that. Okay.
You know that thing in like that big, I don't know if it's a machine or not, like it makes things go to speed of light or something.
Okay.
You know what it's called?
I don't know what it's called off the top of my head.
It's an atomizer ingredient.
It sounds like a particle accelerator is what it sounds like. I'm not sure what type. Okay. Is that it?
How to do that? Like,
Talk about it later. Alright, so make a note though, for that's the wavelength. The crest is the top of the wave. So if it helps you remember like a wave crest, if it helps you think of it, that is like the foamy part at the beaches whenever it's crashing down on the beach. So if that helps you remember it, that's fine. Trough, like our Chris pointed out earlier, it's like a feeding trough for animals, so it has that dipped shape. If that helps you remember it, whatever, helps you remember it, it's fine. Alright, so making out, so the high points are your waves, the low points are called troughs. The wavelength is the distance between any corresponding points on successive waves. Next page. Alright, the wavelength symbol. Know your symbols as a side note. This is your first one. It's that lambda symbol. It looks kind of like an upside down Y, so that helps you to remember it. So lambda, make a note for that one. That one represents wavelength. The amplitude is the measure of the wave strength. It's kind of what we talked about in the homework. That if you have a really tall wave and then a really short wave, which one has more strength? Quentin, I don't think you were in here for this. The tall wave, this is like comparing regular beach waves to a tsunami. The tsunami is much taller, so there's much more strength in it. We measure it though from the midway point to the top, so that's the amplitude. Because remember, it's the back and forth motion. So because of that, you don't measure entirely from the trough to the amplitude, because your wave is going back and forth or up and down equally on both sides. So that's how come you only measure it from the halfway point to the top or the halfway point to the bottom. So that's how come you don't measure it from all the way to the top all the way to the bottom. Alright, anyone have any questions about that? Something through those two a little bit. Alright, frequency, making of this one, this is the number of complete waves that pass by a certain point in a given time. If you have one wave per 1 second, that is a hertz. So make a note for that. The hertz is the SI unit of frequency. So if you have 1,000 hertz, how many waves have gone by in a single second? If you have 1,000 hertz, what is that then? Or how many waves have gone by? I'm not gonna call them Chris right now. Alright, Ethan. If you have 1,000 hertz go by in a single second, or if you have 1,000 hertz, how many waves have gone by? If 1,000 waves have gone by in a single second, so you have 1,000 hertz,
You have
how many waves have gone by?
1,000 waves.
There you go.
Oh,
So
that's
yes,
close.
you have 1,000 waves. Alright, Chris, do you have to see me a class? Okay, you need to fix it. Make sure that
You
you
better
think
fix
it through
it.
because we have to keep going. I can't be having random
You
stuff.
better fix it.
Alright, so make a note. So this is the SI unit frequency. So the SI unit hertz, we got that one. So instead of just saying 1,000 hertz, what prefix can I put in front of it? Alright, Quentin. Alright, instead of saying 1,000 hertz, what prefix means 1,000?
Okay.
Kilo. So you would just say kilohertz for it. Alright, the speed of a wave is simply the rate at which a wave travels. Alright, you better do your first equation for this one. So do make a note for this one. So this one's straightforward, it's not a hard equation. But it's V equals lambda times frequency. Alright, what does lambda stand for?
You're like,
Ma'am?
What does the lambda stand for?
Speed. Oh, what does that stand for? Amplitude, wavelength.
Wavelength. F stands for frequency. So this one is wavelength times frequency. That'll equal the speed. Now, you're booking the two as V. Anyone remember what V typically stands for?
Volume.
Not quite. No. You're right that, okay, yes, we
Velocity.
do use velocity. So if you're talking about how fast something's moving, V stands for velocity. You get a better version of this equation later on. We're just saying, okay, that wavelength, frequency, and speed are mathematically related. That, okay, if you have a wavelength times its frequency, that'll tell you how fast the wave is moving. So if the wavelength is getting larger, but the speed isn't changing, what happens to the frequency? Does it also go up or does it go down if you have to have the same number? Yep, it has to go down because these are inversely proportional. Like for example, you have a wave that's moving 60 meters per second. It's decent. So if you have the wavelength is 20 and the frequency is 30. So for this one, I think that's too high. 20 times 30. 20 times 30 is what? That's 600, right?
yes.
Yeah.
We'll do 5 times 12 then.
You
Alright,
go.
so 5 times 12 is 60. So let's say though that this one goes up to 6. What does frequency have to be then?
10.
10. So it has to go downward. So this is the idea of they are inverse proportional. So again, just the idea for you. Books just pointing out really quick. Anyone have any questions though about that? Alright, so classical theories of light. So here's your scientist and that you need to know for it. Your book's introducing scientists and what they did really quick. Sir Isaac Newton, we talked about Sir Isaac Newton a little bit, but make a note for him that he wrote the book Optics. Now, optic refers to what? Anyone remember from biology?
Sight.
I like,
Eyes. And so because of this has to do with your eyes or with sight or with light in particular. So that's what his book Optics is about. He came up with the particle theory of light. So make a note for him. He says the particle theory of light that the idea of the light can be pictured as a stream of tiny particles emitted by light sources. He basically said light is made up of these substances, these particles, kind of like BBs. So your light bulb is shooting off all these BBs in all directions. Is the idea that he said. He's not quite right, but it was one of those. Okay, that seems like a good idea. He thought that because what happens if you hold up an object against a light source? What's gonna happen? Like for example,
It's gonna block the light.
it's gonna block the light. So that means that light has what? If it can be stopped by a physical object.
energy.
Okay, not just energy.
Light.
Substance.
Substance, it has matter. So Newton said, okay, if you can cast a shadow, then Newton said, okay, light must have substance because you are stopping it, and since you're made of matter, then okay, light must also be made of matter then, because you're casting a shadow behind you. So it's one of those, okay, that makes logical sense. Not quite right on what we know today, but it was a good idea. But since it was what Sir Isaac Newton said, everyone said, oh, okay, light is made of particles. Sir Isaac Newton said it. Okay.
Didn't you graduate college at 14?
A lot of them did. I don't remember if he specifically did, but I know a lot of these young scientists that all graduated early.
I
don't know
graduated from
specifically
Harvard.
if he did.
I graduated high school at 24.
I'm not going to college 'cause I'm
He said
dumb.
you can't graduate from here till 21.
When you got raised, you kicked the
I think it starts at 20. Again, I don't do a whole lot with that. It's not a whole lot with seniors.
Has that ever happened?
We're not gonna talk about that right now because this goes on YouTube. Alright, so just making it though. So particle theory of light. This is the last one, and that's what Isaac Newton came out with. A contemporary of Newton, so another scientist said, I think it acts more like a wave. But since this was against what Sir Isaac Newton said, no one cared what he said. So he just got ignored. So Christian Huygens, make a note for him. So Christian Huygens, it's spelled different. So he has 2 A's in his first name, which is unique. And then his last name is spelled not how it sounds, so be careful of that. So Christian Huygens. Okay.
Do you think his whole family was like maybe scientists, and Isaac has 2 A's, so they put 2 A's in Christian?
Alright, so contemporary Newton, so here's the wave theory
She
of
just
light.
ignored you.
So just make a note of that. And he says that light consists of a series of waves rather than particles. So he said, okay, light moves in this wave pattern is what he was noticing. So you're saying, okay, it acts more like a wave, but again, because he was just ignored, because everyone listened to Sir Isaac Newton, they just ignored what he said. Alright, is it an honest question? Or a real question?
Actually, I take back what I said, because he was born before us.
Is this a real question?
Yes. Okay, so why did they not believe Isaac Newton that he was older? Because he older, he has more knowledge.
Because Sir Isaac Newton was established as like a scientist community,
Isaac
so
wasn't.
not as much as Sir Isaac Newton. Remember, Newton came up with the 3 laws of motion and other things as well. So it was one of those of, oh, Sir Isaac Newton did all this stuff. We're gonna listen to him more.
This might sound really dumb, but aren't those, like, haven't some of those been proven wrong?
I'm sure some of his theories have been proven wrong, but the 3 laws of motion, yeah, we still use those.
Really?
Yeah. And then also, this is one reason why. Okay, if you were to name the colors of the rainbow, what are the colors of the rainbow?
Red, 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 red.
Red,
Did you say
orange,
red, 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 red?
Red, yellow.
red,
That's all I
orange, yellow,
see.
green, blue, purple.
Good job. Alright, how many of you
Quit
heard
your
it with red, orange, yellow, green, blue, indigo, violet?
Obviously, dude.
I have.
Yeah, okay. Occasionally, scientists will flip back and forth on whether or not indigo counts as blue or does indigo its own color. So, a lot of people flip back and forth. Does anyone know why that keeps coming up? Okay.
Because the UV rays emitted off the science and how to change colors, and it looks a lot like blue.
Okay, why is it not, like, why do they stick it as its own category in the rainbow as opposed to just making it blue? Like, why do they keep saying, okay, it's blue, no, it's indigo? But why is it not just a different shade of blue?
It's not
It's
slightly.
not,
It's slightly blue, like slightly.
Yeah, it's like it's an in-between color, but we don't do that for all the colors, like there's in-between colors.
purplish.
Well, there's colors that are always in between them, like a rainbow doesn't come out in like separate bands, there's blurs for all of them, so why would we do it for everyone? What?
Well, there's
Maybe
orange.
rainbows aren't real.
Well, it's because Sir
What?
Isaac Newton, whenever Sir Isaac Newton was working with the prism,
The earth is flat.
he listed it out as there's 7 colors. And so again, because scientists even today still go, maybe Sir Isaac Newton was onto something. Maybe we should keep it as by itself.
Maybe the earth is
And maybe-
flat.
Okay, don't get distracted. And so that's the reason is even like today, when people still bring that up, and the main reason for it is because, well, Sir Isaac Newton said it's its own color. It doesn't matter. But again, that's the reason why you keep hearing that bring up. And again, ultimately it doesn't matter if there's 6 colors of the rainbow or 7 colors of the rainbow. It doesn't matter. But it's one of those occasionally you people keep bringing it up, and that is one of the major reasons is because Sir Isaac Newton said it in his book, and Sir Isaac Newton was so smart, maybe he was onto something. We haven't figured it out yet.
They treat him like a god.
They value old scientists and a lot of people because a lot of these men were really intelligent that whenever their theories get like disproven, it makes them nervous to like fully move on from it. Like Aristotle's teachings were taught for 2,000 years.
And they're wrong.
Yeah, and I would say a good 99% of them are wrong because Aristotle didn't like actually test his theories. He would think things through, but he didn't actually test it. So again, that's one of the reasons why scientists just go, okay, well Sir Isaac Newton said it. Okay, well it's Sir Isaac Newton. And so that's one of the reasons why people have a hard time getting away from these
When
ideas.
did we stop using Aristotle's ideas?
It was around with Sir Isaac Newton's time and Galileo's time. Galileo was one of the major people that went out and like actually disproved a lot of Aristotle's ideas.
How many time was BC, like how much was before BC?
BC's before Christ.
Yeah, I know, how many years?
I don't remember.
Is it like over 100?
I don't remember when, it was, Aristotle was a Greek, so I don't remember specifically for it. But Galileo was in the medieval time period.
You said 2000, and I was like, it was 1600, that's like 400 BC.
That sounds about right. But again, I don't remember specifically for it, because remember Galileo was in the medieval time period with the Roman Catholic Church. He got excommunicated, as a side note, because of
Nice.
stuff like that. Alright, so we gotta keep going though. So, making up right now, so, Christian Huygens, that he came up with the wave theory of light, saying that, okay, light acts like waves too, so they can't be made up of matter, because we don't see wave-like properties in matter, so maybe it's a wave, but he got ignored. Eventually, James Clerk Maxwell, he said, okay, James Clerk Maxwell, he came up with this idea that it acts kind of like electricity and magnetism, so it has terms of an electric field and a magnetic field. They are vibrating at right angles to each other, so this is an electromagnetic wave, or they're oscillating, or they're vibrating at right angles to each other. So your book has this picture. I thought I grabbed that picture. Alright, your book has a picture at the top of the page. Okay, it doesn't matter which one's on top and which one's on bottom, your book just picked it that way. They're not actually green and orange, but your book's just saying, okay, you have the magnetic field coming off one side, and then you have the electric field coming off the other. And so they are intersecting at the points as they're going. I can't do that because my arms have matter and they can't go into each other, but it's the idea of it's going up and down and back and forth at the same time. So, that's the idea of an electromagnetic wave. Make a note of him, that James Clerk Maxwell, he said light acts like an electromagnetic wave that has both properties. It acts like electricity, or electric, and it has magnetism at the same time. So make a note for that one. Now, your book also points out the scientists discovered that light has the speed of light in the vacuum. It never, ever changes. Anyone know what the speed of light in a vacuum is? Raise your hand. Alright, Ethan? Chris?
600 something miles an hour, right?
Not 600 miles an hour, it's much faster. Anyone know? Speed of light in a vacuum.
1 million speed.
No.
Oh, okay.
Alright, anybody else read it?
20 hertz.
Nope. Alright, look at the bottom of page 94. So, it's 299,792,458 meters per second, or we just say 3.0 times 10 to the
You
8.
can't even see that.
It's on page
I
94.
can't even see that, like,
Yeah, no, you can't. That's one reason why, if you turn on a flashlight, you don't see the light come out of it. You just see boom, light,
Do you
and
know,
it's
like,
there.
do you know, like, what the speed is for when the ice stops being able to catch things like that?
When ice, I forget the speed for it, but it's something to where it depends on how large the object is as well. Like if I were to shoot a bullet, you can't really see the bullet moving in the air. But if you were to have a car go the speed of a bullet, you could see it, the car as it goes by, because it's so large. So it has to depend on how large the object is. What?
How fast does a bullet go?
Depending on how fast it is.
Like 120 miles an hour?
I forget how fast it is. It's in the hundreds. I just don't remember the exact speed for it. But it's definitely moving. That's one reason
Doesn't
why.
it depend on the gun?
What?
Doesn't it depend on the gun?
Yeah, it depends on the firepower of the gun.
Yeah, it does as well for it. But yeah, that's the reason why I don't remember the exact like ratios for it. But also again, doesn't depend on it, but light moves incredibly quickly. This is one reason why lightsabers in movies don't work. Like how you see them slowly come out of the lightsaber hilt like that. No, it should be complete all or nothing. There is no, oh, it slowly comes out. Nope, it either is all the way out or it's all the way in. So you should not see it slowly move like that at all, because light moves so quick. Alright, so make a note though, make a note of the speed of light in a vacuum. So 299,792,458 meters per second, or just 3.00 times 10 to the 8. That one also works as well. So speed of light is given a symbol. Now keep in mind, since we're not in thermodynamics, we reuse some of the symbols. So it's lowercase c, since we're talking about speed of objects. Speed of light is represented by c. So I know C represented specific heat in the previous chapter, but that was in the specific area of thermodynamics. So if we're in another branch of chemistry, some of the same symbols get reused. So I'm sorry, I know that's confusing. So bring up C in this chapter, and anytime we're talking about speed of an object, C typically refers to speed of light. Just make a note for that. Alright, just about out of time. Alright, so we'll stop there. You don't have any homework because obviously it's Wednesday. So just make sure that you're reviewing your terms. If some of you that need a good grade in the future, you need to make sure you're studying them now, so that way you have terms and conditions. Like you already have a bunch. This is day 1. So if you start having a quiz on Friday, trying to boost your grades a little bit, you need to start learning them now. You don't need quizzes to help start pulling it down again. So you need to start working on
Why'd
now.
you stop so early?
What?
Why'd you stop so early?
I have like 1 minute.
Like 2 minutes.
I have like 1 minute. Alright, so what do you call the crest to the next crest, what,
Wait,
wait, alright, what do you call the bottom part of a wave, raise your hand.
Crest.
Wave, bottom part, raise your hand.
Trough.
Trough, alright, what do you call the number of waves that go by at a given point, Ethan?
frequency.
Frequency, what is the SI unit for frequency?
No, it's the Lambda thing.
Nope, SI unit,
SI
how do we
unit.
measure frequency? Huts, good job. Alright, who came up with the particle theory of light?
First year, like, that was, I Newton.
Good job, sir. You came up with the wave theory of light, give us even more.
Huygens, whatever his name is.
Huygens, yeah, I know, it's spelled funky, it's spelled weird. Alright, bye, have a good day.
Maxwell came up with the other theory.
Yep, electromagnetic wave.
Have a good day.
Have a good day. Ethan, come see me. Alright. Alright, so again, for this one, because you didn't go through it all the way, you lost credit for it, I'll go back and reevaluate if I wanna give you partial credit for it, but just letting you know for right now, okay? Alright, thank you. Oh, I forgot to do current, and that's what I was doing water. Oh.